We now continue with first-order logic, or rather, we bring first-order logic to its completion. This is going to be the other hard part, or is it the hard part, of predicate logic. It was hard enough in one way to get accustomed to translating statements of natural language into statements with existential and universal quantifiers. But the difficulty there mostly consists in practice. The more you try to translate natural language into statements with universal and existential quantifiers, the more natural that activity will be. You'll get accustomed to the fact that almost all universal statements contain material conditionals, while almost all existential statements contain conjunctions. And it'll feel like a natural thing to say. Of course, when you say some cats are fierce, right, that you're saying there exists at least one cat, there exists at least one entity, one X, such that X is a cat and X is fierce. There's at least one thing in the world that has both these qualities, being a cat and being fierce. And really that's what it means to say some cats are fierce. Okay. But whereas the emphasis in the act of translating into first-order logic is an emphasis on practice, growing comfortable with the material, things now become more like logic. That is, more a matter of learning a few fundamental rules, memorizing them, and then applying them. It's not really a matter of increasing comfort. Now, this ability to start with premises that are all premises, or there exist premises with the universal or existential quantifiers, and to reason in an argument from such premises to a conclusion that itself may be a universal quantifier or an existential quantifier. That is really the apex of introductory logic. What we're going to be doing after we encounter these proof skills is important, interesting, but really an addendum. Okay, we'll do another version of validity when we use truth trees and predicate logic. That you will find is more straightforward, just as truth trees in propositional logic were more straightforward than using the rules of inference and replacement rules. And then we've got a special topic at the end, definite descriptions. But when someone wants to know whether you have studied first-order logic, what they ultimately want to know is whether you can start with some premises and work your way to the conclusion through a set of steps, commonly called natural deduction. Now, the whole point of going from propositional logic to first-order logic was so that we could capture the inner workings of sentences in ways that propositional logic did not permit us to do. Not just a matter of seeing how ands and ors and if-thens fit between complete sentences, but to look at building blocks that are less than a complete sentence. The problem is, how do you apply rules of logic to what is less than a complete sentence? For that matter, how do you apply a rule of logic to something like this? There exists an X such that X is not F. Can we use the rules that we already took such time to learn in propositional logic, or are we going to have to learn a whole new set of rules? After all, it's still the same connectives. But the connectives are inside parentheses. They're governed by these quantifiers. They don't seem to let us move parts around as we did. Well, the real answer, the way I like to think of proofs in first-order logic, is that when we're really doing the proof work, when we're reasoning from premises to conclusions, we will be using the same rules of inference and replacement rules. Once we can get an argument back into propositional logic, there's a way in which all the real reasoning we do continues to be the same old reasoning we did in propositional logic, but we just have to translate out of the quantified statements into something that works like propositional logic, apply the rules we know there, and then, if all is well, translate back into the for all x and the exists x. Okay, we're actually going to turn quantified statements into what is in a way statements in propositional logic. And once you see them in their propositional logic form, they won't seem so off-putting. You'll know how to work with them. Okay, now to do all that, to be able to move back and forth between the structures of quantified statements and the more familiar lingo and language of propositional logic, we're going to have to learn two new sets of rules and a number of restrictions. Let me add, I'm going to be hewing to the methods and following the terminology found in the textbook of Clenks. However, there are many other ways of essentially doing the same thing, even ways that might not look so much like doing the same thing. So, for example, with instantiation, where you'll see me commonly going to the lowercase a as a name. This is getting a little ahead of us, but bear with me. Where you'll see me putting the name a in instead of x. There are many other people doing the same thing, but they'll just use an x. They'll say, but x without the quantifier is now a name. Which is easier? Which is more confusing? Reasonable people may differ, okay? I'm just going to stick to one method of running these proofs because it's less confusing than introducing a lot of alternative methods at once. But that is not to say that this one method is distinctly better, and certainly not to say that it's more correct, more accurate than other possibilities. Okay. I said that there are two sets of rules and a number of restrictions. We can start with the most important restriction, which is that a line in an argument, in order to be worked with in the way that we're now going to say, in order to be a line that you can translate into propositional logic and then translate back, has to be a complete quantified statement taking up the entire line of the argument. That's a slightly metaphorical way of saying it, but you know what I mean. If you see a line of an argument, there has to be a quantifier at the very beginning, and that quantifier has to apply to all the variables inside the parentheses going through to the end of the line. That is, on that same line, you cannot later have a variable governed by a different quantifier. The quantifier or quantifiers at the beginning of the line have to exercise their function over the entire length of that line. Now, by the way, one of the things it means to say that a quantifier is at the beginning of the line, and that's not trivial, is that there cannot be a negation, the negation sign, in front of the quantifier. The very first thing you've got on the line has to be the quantifier itself. And here we come to the first set of rules you have to be familiar with and use really automatically when you're working with first order logic. They are the rules of negation. They're not really hard rules. Why are they not really hard rules? Because the basic rule is a single one. you've got a quantifier in front, when you have a negation sign in front of a quantifier, you can move it through to the other side as long as you change the quantifier. That is, if you've got, it is not the case that for all x, f of x, this becomes, there exists an x such that not f of x. It's not the case that everything is a flower, okay? That means there's at least one thing that is not a flower. It's not difficult at all, right? Nor is the procedure difficult. You just get used to it. You move the quantifier through from, got to stop saying that. You move the negation through from one side of the quantifier to the other, and you change the quantifier. And it works with the existential quantifier. If it's not the case that there exists x such that f of x, then for all x, not f of x. If it's not the case that there exists a unicorn, right? Unicorns don't exist. It's not true that unicorns exist. It's not the case that there exists at least one unicorn, however you want to say that. If it's not the case that there exists at least one unicorn, then what? Then everything there is, you might say, is a non-unicorn. There are no unicorns. What's the difference? There is no difference. If it's not the case that there's at least one, then in all cases, that predicate is not true. Okay? You move the negation sign through to the other side, and you change the quantifier in the process. Okay? It's the same rule, whether you're starting with a universal quantifier or an existential quantifier. Now, some people then refer to the rule as it applies to more complex statements. They say, well, that was the QN, that was the quantifier negation rules, and now we're going to have the CQN, the rule for categorical quantified statements. To my mind, even that is too much terminology. Once you can see, once you're comfortable with the reason, and the reasons are all to be found in propositional logic, by the way. Once you're comfortable with the reasons why the negation applies as it does, in a sense, you don't need to learn the rule. You'll master it automatically, and when you're in any doubt, you'll prove it again for yourself from the ground up, and it won't be any more work. Here's what I mean. Okay, so if it's not the case for all x that f of x, okay, that's the same as saying there is an x such that x is not f. Okay. Now you recall that the overwhelming majority of statements beginning with a universal quantifier are if-then statements. Okay? To say all dogs are happy is to say for all x, if x is a dog, then x is happy. That's one of the fascinating insights, for my money, about first order logic, that we've got these two different logical structures where in a natural language we have a single grammatical structure. The logical structure of the universal statement is an if-then, whereas the logical structure of an existential statement is an and. All right then. So, suppose you have, it's not the case that all f's are g's. Okay? It's not the case that for all x, if f of x, then g of x. So, you take that negation and you drive it through, so that there exists at least one x such that it's not the case that if f of x, then g of x. Could you leave it in this form? You could leave it in this form if you wanted to, if you had a reason to. You don't have a reason to, because when you've got the negation governing a parenthesis, you know, that becomes unwieldy within a proof, and what you really want is to get through the parentheses to have individual propositions you can work with. Fine. But what happens when you negate a conditional? It's very simple, and you've done it 1,000 times by now. When you negate a conditional, all right, just back in propositional logic, we don't need anything fancier than that. If it's not the case that if A, then B, we know that if A, then B can also be written not A or B. Okay, so if you negate not A or B, you get A and not B, which is what you of course get when you negate a conditional. If you say it's not true that if there's gas in the tank, then the car is running, you could also be saying, because after all, you could have gas in the tank and the car doesn't run, right? You could have the antecedent and the negation of the consequent when a conditional statement is false. Okay, so that means that when you have negated the all f's are g, and you get there exists an x such that it's not the case that if f of x, then g of x, you can also write that there exists an x such that f of x and not g of x. If it's not the case that all dogs are happy, yes, then there's at least one dog that's not happy. There is at least one unhappy dog. Okay? And likewise, when you negate an existential claim, if it's not the case that there exists an x, f of x, so that all x is not f of x, whenever these statements beginning with existential quantifiers are more complex, are more syntactically elaborate, they overwhelmingly tend to be conjunctions. Okay, so suppose you have f of x and g of x, and you negate it. It's not the case that there exists an x such that f of x and g of x. You push the negation through to the other side of the quantifier. So, for all x, now you just use De Morgan's. What's fancy about De Morgan's? We were talking about De Morgan's law way, way long time ago. For all x, not f of x or not g of x. But of course, remembering how conditional exchange works, you know that's the same as if f of x, then not g of x. Okay? So, suppose f here, the predicate, it means is a flower, and G means speaks German. And you say, come on, there are no flowers that speak German. It's not the case that there exists something that's both a flower and German speaking. Well, this amounts to saying, for all x, if x is a flower, then it doesn't speak German. So all flowers are non-German speaking, or flowers don't speak German. Okay? That's all there is to it. This is even referred to as a whole set of rules. It's fundamentally one rule. It's the rule that you push the negation through and alter the quantifier. And then the subsequent rule about turning the material conditional into the fx and not gx, or turning the conjunction into a conditional with a negated consequent. Sure, those are rules. Sure, those are worth memorizing. But you know what? If you don't memorize them, you'll just have to figure them out again each time. And each time will take you about a second and a half. Okay? As long as you remember the basic rule about negation, then quantifiers will not cause a problem when they're negated. Mind you, the fact that it's straightforward does not undermine the importance of being able to work with the negation. That is, when you see a negated quantified statement in an argument, you've got to get rid of that negation in front before you do anything else, because the rules we're now coming to simply are not going to apply unless the line begins with either an existential quantifier or a universal quantifier. Okay? The rules will not apply. The rules will not apply unless you're starting with the quantifier. So if there's a negation out front, really the first thing you want to do is get rid of it. So now we're in a proof. We're in an argument. We've got some statements that begin with universal quantifiers, and we've got some that begin with existential quantifiers. Now, as I said, we, in a way, move to a different kind of logic in the course of these arguments. We start with first-order logic, where every statement has a quantifier in front, and then we want to turn those statements into, although they may not look like it, what are, in fact, statements in propositional logic. We work with them according to the rules that we've come to know so well, and then we move back into the syntax, the appearance, the structures of first-order logic. Moving from the symbology of quantifiers into propositional logic is called instantiation. Moving from what is, in effect, propositional logic back to the structure, the symbology of first-order logic is called generalization. Sometimes we've got universal quantifiers, sometimes we've got existential quantifiers. And in each case, we have a type of instantiation and we have a type of generalization. Okay? And these are called UI for universal instantiation, UG for universal generalization, EI for existential instantiation, and EG for existential generalization. Okay, these are the four processes. And so when I said there are two sets of rules, the first set of rules had to do with negation. Set of rules. It's one rule, really. The second set of rule has to do with these four operations. But it's, so you might think, okay, there are four rules. Yeah, except that two of these four operations are so straightforward, are so unproblematic, that the rules are scarcely more than the rule, do whatever you want, okay? That's universal instantiation and existential generalization. When you're doing either UI or EG, you can do what you want. By do whatever you want, I mean the following. Let's take the most unproblematic of all, existential generalization. Let's say you have FA and G of A. For what is A here? And here's the beauty part. when you're talking about existential generalization, there are no restrictions on what A can be. Can it be a name that has appeared elsewhere in the proof? Sure. Can it be a name appearing for the first time? Doesn't matter. Can it be a name? Sure. Okay. But when you've got FA and GA here, the step that we call existential generalization simply amounts to going from FA and GA to there exists X such that FX and GX. Because what is that? Remember that existential statement, the existential quantifier. The existential quantifier only, even though we sometimes translate it as some FRG. Okay. Logically, all the existential quantifier really means, really requires, is that there be at least one. So, right? So if little old a is F and little a is G, it follows, and you know that there exists at least one X such that X is F and X is also G. Which one? Well, A, for example. There might be others. There don't have to be others. That's the nice thing about existential generalization. When you see a single name attached to a given predicate, you're entitled to infer that there exists at least one. You're entitled to go from the language of what is really propositional logic to the language of first-order logic. And let me just reiterate one thing here, or clarify one thing that might be confusing. When I say FA and GA is more or less propositional logic, I know that FA doesn't look like a statement in propositional logic where we have a single letter for a statement. That's true. However, what I mean is you can now you can apply all the rules that you learned about conjunction, for example, to this conjunction, right, in just the way that you did in propositional logic. Okay, so of the four operations, existential generalization is one that you just don't have to worry about. Now, almost as carefree is the life of someone who uses the operation universal instantiation. Universal instantiation means going from for all x, f of x horseshoe g of x, to f of a horseshoe g of a. And the reasoning is pretty straightforward. That is, oh, my apologies. After much habit, I'm accustomed to writing the universal quantifier with an upside down a. A lot of people still do that. Other people just use the x in parentheses. We don't want confusion. The reasoning here is as straightforward, really, as the reasoning for existential generalization. For all x tells you this is true for all the x, or if you're assuming some set like all human beings or all physical objects, something broad like that. You're speaking of all of them. Well, if it's true of all of them, then you can just pick anything at random, any name, let's call it A, okay, and say if it's true for all of them, then it's true for A, okay? If all philosophers are good, then if A is a philosopher, then A is good. I understand that philosopher doesn't begin with the letter F, but it simplifies things here. Those two operations cause no trouble. Why did I just say that universal instantiation is only a little bit trickier? Because sometimes, or many times, we apply universal instantiation planning to go back to universal generalization. And that's when we're going to face some restrictions. Get to those in a second. First, existential instantiation. There exists X such that MX, and you might want to write in a proof MA. Can you just write MA? Can you say, well, there's something that's a mammal, therefore A is a mammal? Yes and no. The problem here follows from exactly the limitation that made it so easy, so permissible to apply existential generalization. An existentially quantified statement is, in a strictly logical sense, a very weak one, right? It's only saying that there exists at least one. You don't know anything else, you just know that there's at least one. That follows directly from all sorts of statements, okay? But given that it's only telling you that there's at least one, you can't just help yourself and say, well, therefore, I know who's a mammal, like the flower on the windowsill is a mammal, okay? It doesn't follow. You know that something, right? Something can go here. Some name can go here. You just don't know what it would be the name of. And so the limitation on the existential instantiation is that you may not have used that letter before in this proof. So and again, other people do this in other ways. There are many different notations. We're just sticking to one notation, okay? When you go from this line of a proof, there exists X such that MX, and you go to the particular one, you give an instance, that's why you're instantiating it, MA, that's existential instantiation. You write after that flag A, flag. Notice the A. That A may not have appeared before this point in the proof, okay? You can't just put any old name in there, right? By looking for a name, a letter in this case, that has not appeared earlier in the proof, you're saying, I make no presumptions about what that thing is that's M, that's a mammal. I just know there's something and we're going to call it A. Okay, so you flag the name that you use when instantiating an existential quantifier, right? So that you don't get into all sorts of logical trouble, that you don't end up making logical errors. This leaves us with UG, the universal generalization. Although this restriction in EI is an important one, you can learn it just like that, right? You just use a new name. The only one of these four operations that has a bit of complexity to it or requires some kind of a rationale is universal generalization. The idea behind universal generalization is this. We can't logically work with f of x. F of x, it's not a statement. It's an open sentence, right? We can work with f of a. All right. And within a proof, we can use FA as if it were a proposition in good old-fashioned propositional logic. But we always plan to go back and turn the whole thing into a universal statement again, right? So, not in this case, but in some other proof, we might have, for example, MB horseshoe GB, and we want to generalize from that and say for all x, if mx, then g of x. Okay, that would be the universal generalization. But when can we do that? We can only do that if the b that we have been using in a proof is a name, but not any particular name. It's a dummy name. Okay, it's like the John Doe, Jane Doe in the law. There's a name there. You're putting it there because that's where a name goes. It's not necessarily the name of anyone or anything in particular. Okay? So the idea is you switch into the language of FA, MB, and so on, and you work with it logically, but there's nothing special about that. There's nothing special about that particular name. So you're saying everyone is either right-handed or left-handed. So let's take Pat. Pat is either left-handed or right-handed. Okay? And everyone who's either right-handed or left-handed has a preference for one of their two sides. And therefore, Pat has a preference for one of those two sides. Okay? Therefore, everyone has a preference for using one of their two hands. Okay? What was I doing there? I was reasoning about everyone, but just using the name Pat as a placeholder. And that really is what's going on with universal generalization. You put a name. Okay, when you first start, you indicate, you flag again this name. You put a name in for the x. You treat the resulting statements as if they were statements in propositional logic. And then, because it has been just a dummy name, you are then entitled to apply UG, to apply universal generalization, and go back to the language of x's. Now, what you do in that instance, what you do is you actually write in the proof. It's a line of the proof. You write flag A. Okay. So strictly speaking, you are applying universal generalization to a sub-proof of the entire proof. You're saying flag A, I'm going to use A for this X now, and then you translate these statements so that they say A instead of for all X. Then when you've arrived at the conclusion to this sub-proof, you move back into the language of for all X for universal generalization. Okay? And that name applies no more. Whether we're talking about existential instantiation or universal generalization, these rules about flagging the names that are used are extremely important if we want to avoid logical errors and some kinds of fallacies that people have fallen into. Okay. Now let's take what is in its heart really a very Aristotelian argument. all C's are M's, all M's are V's, therefore all C's are V's. And if you were studying Aristotelian logic, this syllogism would be known as Barbara. It's the name of the syllogism. Okay. Now, by the way, you can see that this is going to come out valid. If all C's are M's and all M's are V's, then all C's are V's. You may also realize without even halfway thinking about it, that we've got a logical principle to use, a rule of inference that ought to apply right here, right now. Hypothetical syllogism. You've got two conditional statements that can link together to give you that new conditional statement that has the antecedent from one of the conditionals and the consequent from the other conditional. Sure. But remember, you can't apply the rules of propositional logic to these statements with quantifiers in front of them. Okay? So what do? You instantiate, right? We move from the structure of formal logic, from the world of conditionals, into the more familiar world of propositional logic. Then we apply the hypothetical syllogism, and then we come back out. Okay. Different people do it different ways. We flag names on two occasions. When we flag them in an existential instantiation, we write in the right-hand margin, flag A. When we flag for the purpose of universal generalization, we put flag A as the line of a proof. Flag A. And then this just means it's the flagging step for a universal generalization. We've indicated what name we're going to use when we move into propositional language talk. And we've also promised, I mean, there's more than one restriction, but the explicit one is the most important one. The restriction that we will only use this name A within the confines of a subproof. Okay. So we've promised we're not going to let this A run beyond the limits of the subproof of universal generalization. But we've established that's the name we're going to give. We're going to use the name A. So we go to line 1, and because all C's are M's, we can write that if A is a C, then A is an M. Likewise, we can go to line 2, and say that because all M's are V's, therefore, if A is an M, then A is a V. Now, I'm repeating this simply because this is the idea that I find the easiest. If I keep this idea in mind, it makes the proofs in first-order logic the most straightforward. We are now in the world of propositional logic. We were walking outside with formal shoes on. Now we've come home and put on our slippers. And in these more comfortable slippers, we can apply the rules of inference and the replacement rules of propositional logic. Now, you see, we can use the hypothetical syllogism. We've got if CA then MA, if MA then VA, by the hypothetical syllogism, if CA, then VA. Now, who is A? Who is this A who, if A is a C, then A is a V? A could be anybody, right? When we say for all x, mx, we're explicitly saying this holds for all x. But even though here we're referring to some particular A, okay, the name, and this is what it means to flag the name doesn't have to apply to anyone, to anything in particular. Okay, so because we were good and we restricted our use of A so that it did not drift beyond the limits of this subproof, we can now generalize, okay? We mark off the subproof, much as we mark off the limits of conditional proofs. We mark off the subproof, or we discharge the original assumption. And now we're back to saying all C's are V's, okay? We moved into propositional logic, applied the logical rules that we knew, and then generalized. To generalize is to go back into the languages of x's and y's with for all x and there exists x. Now I've already started another one here. This is a proof with but one premise. For all x, and remember, that x, if this is a line we can work with in a logical proof, that quantifier here has to apply, has to exercise its power over the entire line. And it does. This x, this for all x, applies to this entire line. For all x, if bx or wx horseshoe, if bx or wx, then if ax or fx, then sx. Okay? So the antecedent to the main statement is bx or wx. The consequent is itself a complex conditional statement. And then the conclusion we're seeking is for all x, if bx and fx, then sx. Okay. Well, you will not be terribly surprised to learn that the proof of this either requires or works much better if we use conditional proof. Okay. But let's have a look at it first. So we flagged, first step, flag A. We're going to use the letter A. Now, you may notice we have no existential quantifiers in this proof. When we do have existential quantifiers, things are a little trickier. They're specifically trickier in that we always begin with the existential instantiation. Always, or almost always, you put names in for the existential instantiation. Why? Because when you then come to a universal statement and you've got all that latitude, you've got that freedom. What's this going to be? A, B, C, D? It doesn't matter. You're free. But if you plug a name in for a universal statement first and then you come along with your existential quantifier, you can't use a name that has already appeared. Right? So you start with the existential. Okay. In this case, we don't have an existential quantifier, so we flag A and we translate that premise into if BA or WA, then if AA or FA, then SA. Okay, now we're looking ahead. We see that we want to prove a conditional statement. The antecedent of that conditional is bx and fx. We're talking A names now, okay? So we're going to give ourselves an assumption as we do in conditional proofs. That's just the assumption for the conditional proof, BA and FA. You see why we're going to want this, because if we can deduce SA in this proof, well, we're in business. Now in this case, we're going to need both the BA and the FA, so we're simplifying twice. From this conjunction, we get BA, simplified 4, and we get FA, again simplifying 4. But we see that for the purpose of this conditional statement that we want to use, you can see we want to be able to use modus ponens. So we add to the BA, we get BA or WA, and we infer this whole consequent. If AA or FA, then SA. Okay. What's new about this? Nothing. What's new about this? Nothing. These are rules we've been using for weeks. These are just the most familiar rules of inference from propositional logic. After all, logic is logic. Okay? The whole point and the idea behind logic with quantifiers is just to figure out how to be able to use the same rules that we learned when the statements have this more complex new form. Okay. Now we need the antecedent to this conditional. That shouldn't be hard to find. We already have f of a. That we get by adding to line 6. And so modus ponens, when applied to 8 and 9, gives us SA. Now, what do we do next? Okay. Remember how when we did conditional proofs and indirect proofs, there was this idea the lines don't cross. Okay. You complete a subproof before completing the proof it's embedded in. So too here. On the basis of 4 to 10. Why? We assumed BA and FA in line 4. We derived SA by line 10. And so we can conclude if BA and FA, then SA. That's a conditional proof. That's the conditional proof, the subproof really, that took us from line 4 to line 10. But that's not the conclusion we wanted. We wanted this universal statement. And so by universal generalization, we deduce that desired conclusion. What entitled us to deduce that conclusion? Simply the fact that while we were in what is really, strictly speaking, a subproof, while we were in that subproof, we only used the letter A within the subproof. We didn't talk about anything else. We didn't use A for another purpose, right? We were just saying, well, if it's true for all X, it could be true for this one X. Let's call it A. And so we used A as that dummy, as a prop, let's say, until we found the right form of the conclusion we wanted. At that point, and because we had used A only in this particular fashion, we were entitled to generalize, to apply universal generalization, which got us the desired conclusion. Now, there are yet more examples we can practice with. Okay, the existential quantifier adds some other conditions, but nothing is as complex in its operation as the use of flagging of a name in order to make universal generalization possible. And once you've got the hang of that, why then it's not just that you can do all these proofs in first order logic, it's that, you know what, you already could do all the proofs in first order logic even before you knew that you could. Okay, so we've learned something very important and new, and yet we've relearned something that we always already knew.